So hello, my name's Pat. I'd like to welcome everyone to Basic Principles in Chemistry today. We're going to be going over some material that you would cover in the first week or week and a half of Introduction to Chemistry, that's 1305, or General Chemistry 1, that would be Chemistry 1311. Some of this may be material that you already know, some of it may be material that you haven't gotten yet, but it will all be material that will be essential as you go forward in chemistry. We're going to start right now. I want to make sure that this is visible. Everyone can see welcome on the screen, hopefully. So here's our welcome. Let's start with some basic principles of chemistry. The first is that everything is made of matter or stuff. And so it's all made of matter. We have matter, which is something that occupies us, has mass, and takes up space. So some of our basic subatomic particles are the following. These are important. You have protons, then you have neutrons, and then you have electrons. Now it's important to know not only the charge of these, but also to know the mass and to know their location. So protons, thinking pro being positive, that has a positive charge. The complement to the proton is the electron, which has a negative charge, which is the exact same amount, but it is negative. Now, neutrons, as the name may give you a clue, they are neutral. They have no charge. Then we come to mass. Now, mass, a proton has a mass of 1. We're talking about AMU, which is atomic mass units. And the more particles that the atom has, the more the atom will weigh. And that would also go in to say that the more the atom weighs, the more a mole of that atom weighs. We'll talk about what a mole is later. But for right now, let's keep in mind that a proton has an AMU mass of 1. A neutron has an AMU mass of 1. And an electron has, for our purposes right now, it has no mass. Now, this is not exactly true, but you won't factor in an electron's mass until you get to Einstein's equation of E equals mc squared. Energy equals mass times the speed of light squared. That's an equation that you would see at the end of Gen Chem 2. And to give you an idea of how little electrons weigh, it would take 10,000 electrons equal the weight of 1 proton or neutron. Now, the last thing that's important about these subatomic particles is that protons are found in the nucleus. Neutrons are also found in the nucleus, but electrons orbit the nucleus. So this can be a handy chart as you go forward, as they ask you some basic questions in chemistry. Also, if you're in biology, typically the start of biology is also going to ask you some basic chemistry questions, but that are going to deal with protons, neutrons, and electrons. One last thing about these subatomic particles, it's important to know that protons, your number of protons, will equal your atomic number. Now, your atomic number is generally how things are arranged in the periodic table. You have hydrogen, which is symbolized by H, and that has an atomic number of 1. Helium, which has an atomic number of 2. Lithium, which has an atomic number of 3, which means that hydrogen has 1 proton. Helium has 2 protons. Lithium has 3 protons. So your number of protons is the same as the atomic number, and if you have a periodic table, you can follow that out 1, 2, 3, 4, and so forth. The next important piece is that your number of protons plus your number of neutrons, together they will equal what is called your atomic mass. This is showing that electrons are not factored into this. Let me give you an example of this. We have the symbol for carbon is C. So when you have that C, what you would write would be carbon 12. You've probably heard of carbon 13 or carbon 14 if you've ever heard of carbon dating. This number up top in this sort of layout, this is your atomic number. Now, because it's carbon, and basically we use the number of protons as the definition for what the element is, you do not have to write this in the bottom, but sometimes they will also write in the bottom 6, which is showing the atomic number, versus the atomic mass is written on top. That would be, so you could work out, they could give you a problem that would be something like they could ask how many neutrons are in here. So we could say, well, we know neutrons plus protons equals 12. Because I know that it's carbon and all carbons are 6, neutrons plus 6 equals 12. Subtract your 6, subtract your 6. And you know that you would, in carbon 12, you would have 6 neutrons. If you had something like carbon 14, you would work it the same way. You'd say neutrons plus protons equals 14. Neutrons plus all carbons. If it doesn't have 6 protons, it's not a carbon. So neutrons plus 6 equals 14 minus 6 minus 6. So carbon 14 winds up having 8 neutrons. Last piece of information to provide is that in a neutral atom, your protons, your number of protons, will equal your number of electrons. This means that if your carbon is perfectly, if it's a neutral atom, if you have 6 protons, you have 6 electrons. If we were to look at sodium, which has an atomic number of 11, a mass of 23, they could ask you about sodium, and they could say, well, how many protons does sodium have? Well, all sodiums have 11, so it has 11 protons. How many neutrons does it have? You would have to say neutrons plus protons, which is 11, equals 23. Subtract your 11, subtract your 11, and that tells you that your neutrons are 12. Because there is nothing written up here, that says that you can also, from this given information, because it does not have a positive or a negative written above as a superscript on the right-hand side of the symbol, we can also say that this must have 11 electrons. So those are the basics of our subatomic particles. This is one of the things you cover in the very beginning. I'd now like to talk a little bit about the evolution of the idea of the atom. And I will be happy to show any of the things that I've written at the end of the session. We will certainly go ahead and do that. So our first idea of the atom we are going to talk about is going to be Thompson's idea. Now, Thompson's atom was, in a sense, he thought it was a giant, large kind of mass that had an overall positive charge, and then buried in here would be little negative charges that worked out, and that the negative charges balanced the positive charges. So the most common phrase or allegory for this is this is what's called the plum pudding model. Now, plum pudding, we don't have plum pudding. If you're from England, you probably know what plum pudding is. But what we do probably have, and what you are probably familiar with, is the idea of Jell-O with pieces of fruit in it. So basically, it would be everything was solid, and you had little small negative charges scattered around that balanced the overall positive charge. So plum pudding is the phrase they use. But here in the United States, let's just think of fruit in Jell-O. So that was Thompson's idea of the atom. Now, this idea was not exactly correct, and they did a very famous experiment where they had basically a projector that shot alpha particles at a piece of gold foil. And the idea that we were thinking was, if this was solid, the particles should come straight back. They should hit the foil and not penetrate the foil. Very thin sheet of gold foil. But what happened was most of the particles would pass through the foil, and they wouldn't hit anything. You would have a few particles that would travel, and they would be diverted. They would kind of veer off as if something was repulsing them or something was reflecting them, so they'd be slightly diverted. And then you had an even fewer number of particles that would just travel. They would come right out here, and they would reflect back. So we came up with Rutherford's idea. And the fact that most of the atoms pass through let us know that he came up and he was convinced that what was the case was you had a small, very densely packed center, and then some of these alpha particles would be reacted with the charge of the center, so they would divert. Most of them would pass through, but occasionally one would hit directly and come right back out at the projector that was projecting these little alpha particles. So his idea of the atom is now going to take into account that most of these atoms are empty space. And he came up with the idea that you have a small, densely packed center that has a charge that will reflect some particles that come by it. And then around that, you have other pieces that are orbiting this. So almost like the standard sort of version of an isotope or radioactivity.
We can't see the bottom. There we go.
There we go. So this is the diagram here. This is what Rutherford came up with, that these were all orbiting. Now, he was not quite correct, but he was closer than Thompson because he understands that it's densely packed in the center. It has these atoms circling around it. The next best version, and the last one we're going to talk about, is Bohr's model. Bohr came up with the idea that, yes, you have this densely packed center that is protons and neutrons, and they are densely packed in there. They're tightly packed in the center. And that will be our nucleus. But then you have atoms, you have electrons that orbit outside the nucleus, almost like planets. And these atoms can be excited into different energy levels or different shells. Now, without going too much into what will be a discussion next time, what happens when these atoms become excited into a different energy level is, if you put energy in, they excite to a different level, and when you take that energy out, they fall back down. They emit a little packet of light called a photon. Most people, if you've heard of photons, it's probably been in Star Trek, but it is an actual real thing. It does have an energy, and it has a wavelength, which is why we may see it as visible light. So we started with a solid atom when we had Thompson. Then we got to Rutherford, who understood that it was mostly empty space with electrons orbiting outside. And then Bohr came up with this sort of solar system model where you have this densely packed nucleus in the center, and you have electrons that will orbit in different shells or different energy levels. The next thing to talk about, and remember, I'll come back to this if anybody has any questions. The next thing to show is that we need to talk about what are physical properties and chemical properties. So for our physical properties are basically ways that you would describe a compound. So physical properties would be something like color, density, electrical conductivity, things like that, versus a chemical property. A chemical property, that comes down to, it tells you how the element or compound will react. If you can describe something by visually observing it, that's probably a physical property. Chemical properties are talking about, well, if you take hydrogen and you put a match to it, it'll burn. That's a chemical property of hydrogen. So that's chemical and physical properties. The next thing to talk about are extensive properties. And intensive properties. Now, extensive properties are related to the amount. It is related to the amount of the compound that you have. Compound, element, whatever it is, if it's an extensive property, it's going to be related to the amount that you have. An intensive property is not related. It's not related to the amount that you have. Let's talk about some examples. Two big examples for extensive properties are going to be mass and volume. Mass and volume will change the more you have of something. The greater the mass, the greater the volume. That also gets into when we talk about heat. Heat would also fall into this. But intensive properties are things that are not going to change. If you have sulfur, sulfur is always going to show up and its color is yellow. It doesn't matter whether you have 1 gram or 18 grams. The density will always be the same. Density is an intensive property. Yes, something weighs more, but density is generally given as, generally you have a mass over a volume, and that remains consistent. The more mass you have, the more volume you have. There's a famous story about Archimedes, who was given a crown, and the king wanted to know if it wasn't a real crown, if it wasn't real gold, and he worked out a way using density to determine, without destroying the crown, that, yeah, you got cheated. They cheated you. It's not real gold. So density is a constant mass over volume. It's not dependent upon the amount. Two last things about intensive properties would be your boiling point and your melting point. Think about water. Water at sea level is always going to boil at 100 degrees. Now, you may need to apply more heat to get more water to boil, but water is going to boil at sea level at 100 degrees. So these are intensive properties. They don't change with the amount. Extensive properties do change with the amount. Now let's talk briefly about the common metric prefixes. We also have I'm going to post right now a link to something that is online. You don't have to copy this down, but you're welcome to pull it down and print it out. I think it's very handy in the beginning if you're not familiar with the metric system. This is available online through the Learning Labs, through ACC. So that will give you a link to all the metric prefixes, but I'm going to talk about the common metric prefixes. These are going to be the ones that you are going to see in chemistry. The first one is going to be kilo. And kilo means 1 times 10 to the third. So basically that means 1,000. Then you have another series. I'm not going to worry about the other series, but it is on that sheet. Then you have your base units. Our base units are going to be meter, liter, and gram. I don't think you're going to need to know it, but the base unit for time is second. You can have kiloseconds, you can have milliseconds. You've probably heard of milliseconds. But you can have kiloseconds, milliseconds, and so forth. But these are your base units. And then we can have a centi. That means 1 times 10 to the negative 2, which could be written as 0.01. You can have milli, which you've probably heard of milli as in millimeters or milliliters. That's 1 times 10 to the negative 3, which is 0.001. And the last two I'm going to talk about would be micro. You may not wind up using micro in chemistry, but it definitely gets used in biology. So micro is going to be 0.000001. And then our last one, or we can think of it as 1 times 10 to the negative 6. This is 1 times 10 to the negative 3. Sorry, I already wrote that. 1 times 10 to the negative 2. Our last one that you will see in chemistry is nano. You won't see this until 5 or 6 weeks in, when you start talking about packets of light. You start talking about wavelengths and frequencies. And that is 1 times 10 to the negative 9. I'm not going to write that out as a bunch of zeros, but 1 times 10 to the negative 9. If you think of kilometer and mile as related, the Old English standard that is related to nano is written like this. It's an A with a little circle on top, and that stands for angstroms. And that is 1 times 10 to the negative 10. This is not a metric unit. I'm just giving you that as something that is vaguely related to nanometers. But these are the most important prefixes to understand. The list of all the prefixes, will be on that sheet that I provided. So now we're going to get to significant digits, we're going to get to scientific notation. Now, scientific notation is handy because you're dealing with very large numbers typically in chemistry. And for our scientific notation, our important thing to keep in mind is here, let's imagine that this is our decimal point. And then we have our ones place. We have our tens place. We have our hundreds place. And we have our thousands place. I'm just going to write 1,000 right there. And then on this other side, this would be our tenths. This would be our hundredths. And this would be our thousands. When we convert something from our standard written form that we're used to, like say 26.2 miles or something like that, when we convert, say, if we had 26.2 and you wanted to convert it into scientific notation, the standard way to say scientific notation is to put one digit to the left of your decimal, and then put your remaining digits on the other side of that decimal. Then you're going to say times 10, and this is where this is sort of going to become like a number line. In math, anything that's to the 1 is 10 to the 0. Anything that's 10 is basically 10 to the first. Anything that's to the 100 is going to be 10 to the second. Think about 10 times 10, that's 100. Anything that's to 1,000 is going to be 10 to the third. You can think of that as 10 times 10 is 100 times another 10 is 1,000. On this other side, where you have positives when your values are greater than 1, on your other side, your values are going to be negative because they're less than 1. This becomes 10 to the negative 1. This becomes 10 to the negative 2. And this would become 10 to the negative 3. The pattern would continue on out. So 26.2 would become 2.62 times 10 to the first. If we had another one, let's say we had 142.3, we would convert that, we would say 1, because you only want to have one digit to the left of your decimal. Then you're going to say 423. You're going to say times 10. Now, because you're in your hundreds place, you're going to say times 10 to the second. Let's do one that is less than 0. So let's imagine that we're given that we have 0.0625, and we want to write that in scientific notation. We are going to write that as 6.25, because in proper scientific notation, there's always one digit on the left of the decimal, the remainder are on the right. And because you are 1, 2 places away, that is going to be times 10 to the negative 2. So this is scientific notation, getting back and forth from standard form to scientific notation. Now, when they ask about significant figures, this bothers a lot of students in the beginning, but it's just a way in science of showing how accurate you're being. Significant figures, when you determine your number of significant figures, you're looking at the number of digits in your data. You would not use a conversion to determine significant digits. Like if you were going from inches to centimeters, you wouldn't use 2.54 to do that. You would only be using the given data. And your determining number of significant digits in your answer is going to be dependent upon what operations you're doing. So if you're doing multiplication, or division, that's the easier one to keep in mind. I think it's very easy because we're going to think about multiplication and division. You are limited by the smallest number of significant digits in your data. So let's say that we have 42, we have, say, 36.3, let's say we have 123.4. And if you are multiplying or dividing, because you only have 2 digits here, your answer should only have 2 digits in the end. That's because in science, if we were to say 3, let's do this one. Let's say if we were to say 3.6 times 7.2, When we multiply that out, we have 25.92. In science, that is implying that you are accurate out to your 100th place. You're not accurate out that far. So science is very concerned about showing the accuracy, not inflating or trying to fudge the data in any way. So we fall back on 2 digits in both of our values. Our final answer should be 2 digits. So this would be reported correctly as 26, and we would stop there. Now, the one that bothers me more is addition and subtraction. For addition and subtraction, we are looking at our last common decimal place. Your last common decimal place determines how many digits. Last common decimal place determines how many digits. So let's say we had values like 7.20, 4.213, and we had 10.1. We would go ahead and find our answer. And my suggestion is if you are working, say, in a classroom or doing a test, I would show everything, and then at the end, I would round to the appropriate number of digits. This would be a 5, and then we would add all this together, which would be 21. But our last common decimal place was this 10th place. So our answer would be written out as 21.5 because we are doing addition and subtraction, and you go to your last common decimal place. Last little thing about significant digits is we're going to talk about rounding. Now, this is definitely something you want to talk about, rounded numbers. You want to ask your professor. Generally, we are used to, if you've ever paid taxes, if you've ever seen FICA, FICA will take out like 6.2357 cents or whatever. Well, we know if we sit down and do that, what they took out was they took out $6.24 because the government never rounds it in your favor. They always get their 0.357 cents. And since they can't give you the remainder of that, they just round up and they take that fraction of a penny from you. But in science, we're very concerned about showing accuracy. So some professors will just use the definition of when it's a 5, you round up. When it's a less than a 5, you round down. But this is one you would want to ask your professors in class, because what we do, if we have 24.5, because this is even, you round down. Because our number before our 5 was an even number, you'd round down. So you would report this, if it was to 2 digits, you just report it as 24. But if you had another number that, say, was 29, or say it was 27.5, because this is odd, now you round up. So you would report this as 28. Now, this is a very, very technical way to look at it, but it is the way they do it and the way your professors will want it done in class if they're being extremely precise. Typically on the first test, they're very concerned about precision. As you go on, if significant figures are something that bother you, just keep in mind that the first test is where they're really going to test you on that. But you would definitely want to ask a professor about the rounding rule. Ask, well, if it's an even number before the 5, do we round down, or do we just always round 5 up? So that will vary from professor to professor. So you'll need to ask them about that just to be sure. Now let's talk about one of the first things. I don't know if you've had this yet, but we're going to talk about dimensional analysis. So for dimensional analysis, this is a way of solving problems and moving back and forth in different units. If you are going into nursing or medicine, you will use dimensional analysis to figure out dosages. If you wind up going into physics or doing some more physics, you'll be given a series of different units that may work out to be a Newton or a slug or something like that. But dimensional analysis is really not that bad. So let's take a pretty standard equation. Let's say that we're given a density of 13.6 grams per, let's say, centimeter cubed, because when it's density, it's always a mass over a volume. And they want to know what that would be in pounds. We'll say pounds per inches squared, or sorry, inches cubed. So what you're doing is you're going to change this. You're going to start with 13.6 grams on top. You're going to start with centimeters cubed on bottom. Now, because grams is on top, we're going to put grams on bottom, and this goes back to the old mathematical idea of if I have 42 over 42, that's a 1. If I have 3.6 over 3.6, that's a 1. If I have 123 over 123, that's a 1. If you multiply anything or divide anything by 1, that will not change your value. So once we have one unit, the unit on top and the unit on bottom, that unit cancels and goes away. So when you start dimensional analysis, whatever's on top, to cancel it, it's going to need to go on bottom. So because I have grams on top and I want to get to pounds, I'm going to use my conversion. Now, you'll be given conversions. I do this, so I happen to know the conversion is 454.5 grams is 1 pound. So now I have canceled my grams. I have my pound reading on top. Now, because this is centimeters cubed, I'm going to have to write centimeters up on top 3 times. 2.54 cm is 1 inch. 2.54 cm is another 1 inch. And 2.54 cm is another 1 inch. So centimeters, 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 that's 3 centimeters. That cancels all 3 centimeters down here. And when I get to the end, what I have is I have pound and then inch, 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 which gives me pounds per inches cubed. And that gives you your value. We can do this with another problem. I'm going to do this with, I'm going to do this with math right quick. We're going to do this. Let's imagine we're on the Autobahn. Now, you've probably heard on the Autobahn that there is no speed limit on the Autobahn. There is, however, an advised speed limit on the Autobahn. And our advised speed limit on the Autobahn is 130 kilometers per hour. You can go faster in some places if you want to, but 130 kilometers, that's about driving speeds on Mopac, where that's what we're going to find out, at least in the fast lane. When you see per, you can think of that, we can write that as 130 kilometers over an hour. When you hear something per, whatever comes after the per is what's going to go on the bottom. Like if you were to give a drug, if you were supposed to say give 2.5 grams of tegamin per kilogram, you would put 2.5 milligrams of tegamin over 1 kilogram, and then you'd work out how much the person weighed to give them how much tegamin. So because we have kilometers on top, I'm going to say, well, I know, and this is just from running, I know that 1.609 kilometers is 1 mile. And I could get really fancy and I could change it out into seconds here. And if I wanted to get to say kilometers or let's say meters per second, let's find out meters per second because that gives us a little bit more to work with. So I have my kilometers.
Hey, Pat.
Which is, yes, sir.
Can you move it down just a little bit? Thank you.
Okay. So we have kilometers here. I'm now going to say, well, I know that 1 kilometer, or I can say that I got 1 mile. I'm going to say this is 1,000 meters. Actually, let me start this again since I'm going to meters per second. 130 kilometers, 1 hour. We'll say 1 kilometer, 1,000 meters. And now I'm going to say 1 hour on top. They don't have to be right next to each other. Kilometers canceled here. Now I have an hour that's going to cancel here. Well, I say 1 hour is 60 minutes. And 1 minute is 60 seconds. So our minutes will now cancel here and here. And we are going to be left with what we wanted, which is meters per second, meters per second. Multiply all the way across the top. So I'm going to get out my calculator and say 130 times 1,000. Get my number on top first. So we have 130. Calculator just kaput. So I have 130,000 on top. And on bottom, we would have 1 times 60 times 60. That's going to give me 3,600 on bottom. And say 130 divided by 3,600 tells me that I'm going 36.1 meters per second. Now, because there's no decimal at my 130, I'm going to say that 0 is not significant, so I would report this as 36 meters per second. Interestingly, I will just say that when we're going to work this in miles, it winds out that 130 kilometers per hour, that comes out to a recommended highway speed of about 81 miles per hour, or basically what you can do on I-10 once you get out west of Junction. So 80 miles an hour is their recommended. That doesn't mean people all drive that. They certainly don't. But, you know, the idea that you can just drive at incredible speeds on the German Autobahn, while that's true to a degree, that's not recommended. The last thing I want to discuss is going to work in with dimensional analysis, and that's going to be our concept of molarity. This is going to be very important in chemistry. Molarity is moles over liters. It's a form of measurement of it's a form of concentration. Now, a mole is related to Avogadro's number. Just like a dozen is 12, of 1 mole, if I have a mole of pennies, I have more money than Bill Gates. I have 6.022 times 10 to the 23rd. It's generally rounded for our purposes 6.02 times 10 to the 23rd. This is really big. To give you an idea of how big it is, if you have a mole of pennies and each penny is 1 millimeter thick, and you were to stack them on top of each other, you would be able to get to the nearest star other than our sun, which is Alpha Centauri, which is 4.4 light years away, 9.5 times. So that's something that's 1 millimeter thick. That's just pennies. But we talk about having 1 mole. If we had 1 mole of hydrogen, that basically weighs it. Hydrogen's mass is 1 AMU, so its molar mass would be 1 gram per mole for hydrogen. That's a lot, but these atoms are so very, very small, this is something that you can have. If you had 1 mole of helium, helium's mass is 4 AMU, and its molar mass becomes 4 grams per mole. Lastly, if we were to have water, if we were to have H2O, we would say, well, that gives us 2 hydrogens, 2 times 1. That gives us 1 oxygen, 1 times 16. I'm pulling these from the atomic masses that are on the periodic table. I do this so I know it. You're not expected to know it, and you'll be given a periodic table. So I'd say 2 plus 16, that gives you 18. So the molar mass of water is 18 grams per mole. So if you have a pint of water, which is about 1 gram per milliliter, you have almost a mole of water molecules. I'd like to do one molarity problem with you to show the relationship between moles, volume, and molarity. So let's say we have 2.5 molar concentration of some compound. And we are given, let's say we are given 450 milliliters of that compound. What we can do is we can say, well, this capital M is the same as moles over liters. We can say 2.5 moles per liter times the number of liters we have, and we're going to convert from milliliters to liters. Quick conversion from milliliters to liters. When you go from milliliters to liters, move your decimal point 3 places to make the number smaller. That's just a quick conversion. You can also do out the math of it. But to me, the fewer times my fat little fingers hit the calculator buttons, the fewer chances I'm going to make a mistake. So I'm going to say 2.5 moles per liter times 0.450 liters. Now that I have liters on top and bottom, my liters cancels. And what unit do I have left? I have the unit of moles left. So if you are given a molarity and a volume, you can find out how many moles you have in the end. This will become, you will use this as you go forward, maybe not this week, but in the following weeks, and when you get to stoichiometry, and certainly when you get to acids and bases, this becomes very important. But this relationship of the idea that you can have a molarity times a volume, and that can tell you how many moles you have, that's going to be key and critical as you go forward. Now, just a quick refresher of what we've done, where we talked about today, and then I'm going to open it up to questions. We talked about our different particles of protons, neutrons, and electrons, what their charges and masses were. We talked about protons equaling the atomic number. We talked about protons and neutrons being atomic mass. We talked about in a neutral atom, protons equal the number of electrons. And the more protons and neutrons you have, the more your particle is going to weigh. That'll be information that you'll be given on a periodic table. Then we talked about Thompson's atom, which was the plum pudding or the fruit and jello idea that was incorrect because most of the atom is empty space. Rutherford gets that idea right, but then Bohr improves on it, realizing that electrons exist in specific energy levels or shells. And he's the one who comes up with the solar system idea. We then talked about our significant viewing from scientific notation. 10 to the 0 is the 1, 10 to the 1 is 10, 10 to the second is 100, 10 to the third is 1,000, and then -1, -2, -3. Negative exponents are signifying values of less than 1. We talked about determining significant figures. Multiplication or division, it's easy. You're limited by the number of significant digits in your data, the smallest number of significant digits in your data. Addition and subtraction, it's best to line everything up and go to your last common decimal place. We mentioned rounding. Remember, technically, if the number before the 5 is even, you round down. If the number before the 5 is odd, you round up. But this is definitely one of the things you'd like to ask your professor just to be sure they're following those rules. We then talked about dimensional analysis. Remember, if something is cubed, you'd have to do it 3 times. If something is squared, you'd have to do it twice. Let's see, we talked about, let's see, what else? We talked about molarity, concentrations, the relationship of moles over liters, dimensional analysis, and how if you have your molarity and your volume, you can find your number of moles. So here I am. I don't have anything more today. If anyone has any questions, they're welcome to ask questions now. If anyone has, you can welcome to unmute or ask in chat. But I appreciate everybody being here today. I'm sorry we went a little bit long, but I hope it was helpful. I hope to see you again. Chemistry is a lot of fun. So, and if you're good in chemistry, it can be very helpful in other fields. One of the jokes I like to rib some of the physics folks that I work with is the reason they created a Nobel Prize in chemistry is because they got tired of the chemists winning the physics prize. And that goes back to the fact that Marie Curie won a Nobel Prize in physics, and the next time she won her second Nobel Prize, she won it in chemistry. But there is overlap between physics and chemistry, and there's certainly overlap between between chemistry and biology. But I think if you stick with chemistry and you follow some few basic concepts, you'll find it to be very useful in a lot of the sciences you may wind up taking while you're here at ACC, or if you decide to pursue your education at other locations. I thank you guys for being here today. I will be sticking around till 7 o'clock if anybody has any questions. And you can also find me. I'm a tutor. I usually work at South Austin Learning Lab. Not that there's any particular campuses anymore, but that's where I usually am. And I hope to see you guys again. Jose, should we stop recording now? Yes.